Hey everybody. So we're going to talk about sequences today. And so let's just jump right in. In some sense, sequences are very simple. As with most of the things we do, we eventually complicate the simple. But let's just start here with what a sequence is. A sequence is an ordered list of numbers. Really, I should say it's an ordered list, but the only sequences that we're going to look at our list of numbers. Okay, so ordered is a pretty important word in there because it means it has a particular order. Like if our list was the numbers 1, 2, 3, that's a different sequence than 3, 2, 1, right? It's not the same when we talk about a set of things. Um, the set 1, 2, 3 is the same as the set 3, 2, 1 because then we're just concerned with what are the things in this set. But here we actually care about the order. Okay, we will talk later on in another video about series, but I want to make this clear right now because in common language, the words sequence and series are more or less interchangeable, but mathematically they are related, but completely different things. A series, the easiest way to say it, is a sum of a sequence, right? So sequence is a list of things, a list of numbers, and then if we add them up, that's our series, right? So it's the difference between 1, 2, 3 and 1 + 2 + 3, right? Those are two very different things. So we're starting with sequences. We'll get to series later, but I want to start that division right now. That noting the difference between them because it's really easy to confuse them since we use them pretty interchangeably in regular life. So when we write down a sequence, if we want to talk about an abstract sequence, we often put it in little brackets, and we can just note each element of the sequence something like this. A1, A2, A3, right? The first part of the first element in the sequence is A1, the second one is A2, the third one is A3. When we have a little ellipsis like this, those three dots, it just means this sequence goes on forever. Sometimes we might have a sequence that's finite length, right? And we could say something like this, right? It goes up to b sub k. Maybe that's 10, maybe that's 50, whatever it is, but some number that you're saying how long the list is, okay? So that's how we represent a sequence abstractly. Just like when I want to talk about a function, but I'm not talking about a specific function, I might write f of x. For a sequence, we might write something like this. We're talking about some sequence. But let's give some examples of some concrete sequences. Maybe maybe the most famous sequence there is, um, the Fibonacci sequence. Seems like more people have heard of this sequence than any other. Goes on forever. We'll come back to that one a little later. And let's do this sequence: 5, 10, 15, 20, and so on, right? So I've left the brackets off in this case. We should have the brackets there, but we'll find that we often write them down without them, just depending on the context. And in this case, I want to do something with this, so I'm leaving the brackets off for the moment. You can see that I hope when we look at this sequence, we kind of see what the pattern is. But I want to use it as an example. The pattern is not always so obvious. And even if it is, it's sometimes nice to write our sequences in a more compact form or explicit form. That's not quite the right word I'm looking for. But in any event, if we notice this, this is going to be 5 times 1. Right? This is 5 times 2. This is 5 times 3. This is 5 times 4. And on and on and on. With that in mind, we sometimes write what we would call the general term, the nth term of this sequence, right, would be 5 times n, right? So sometimes we might write that in our sequence, right, that we've got this, throw the brackets on now, that you kind of set up the pattern, but you might also write this explicit formula. With that formula, 5n, I could tell you any position in the sequence. The 500th element in this sequence is 5 times 500 or 2500, right? So that formula gives us a way to compute any of the elements of our sequence. You'll also see it written sometimes, right? We can get more compact. We might just write 5n, right? This is just saying the sequence that's made by writing 5 times n. We usually want to be even more specific and let people know that n is going to start at 1. It doesn't have to. We'll find out there's some times where we want to actually start at 0. We call this our indexing, right? So our indexing, and in this first example, A1, 2, 3, the 1, 2, 3 are indexes. Sometimes we start our indexing at 0. So the first term or the 0th term. And that can be a bit confusing. There's good reasons for it. I think one really good reason for it is further on down the road, many videos from now, one of the kinds of sequences and series we'll look at have to do with polynomials. And so that 0th term will equate to the constant term of a polynomial. And then the n equals 1 term will be the degree 1 term, and then the n equals 2 will be the degree 2 term. And so you want to start at 0, not 1. And it's nice to have the index matching with the power of the term. But in any event, when we write something like this, we often, unless there's some, unless it's implied in context, we might write something like this. This is what I'm telling people is we're starting with n equals 1 and going to infinity, right? Or if I wasn't doing an infinite series, I might write something like from n up to 100, right? This would be the first 100. Doing from n equals 1 to 100, so 100 terms from 5 to 500, jumping by 5. Okay, so that's some notation. Let's see. Let's just look at a couple more kinds of, or examples of series that we might see. We might write the following series. Here's another notation we might see. The a sub n is equal to 2 to the n. Similar to what I did above, it's just telling you I have a sequence of a's, a sub 1, a sub 2, a sub 3, and so on. And I'm telling you the form that each one of them takes, right? And again, I might write something like for n equals, let's start this one at 0, 1, 2, something like this, that lets you know how the indexing is going to work for this. So with this in mind, let's write this out explicitly, right? So let's take our time with this, even if you maybe perhaps see where this is going already, it's still good to see how we can take our time when it gets more complicated. So when n equals 0, we get 2 to the 0 equals 1. When n equals 1, we get 2 to the 1 equals 2. When n equals 2, we get 2 squared is equal to 4. Do one more. When n equals 3, 2 cubed equals 8. And so this leads us to the series, the sequence, there I go, confusing them. That goes 1, 2, 4, 8, 16, and so on, right? And so, again, we've got this explicit formula, a sub n equals 2 to the n, that would let us know how to compute any term, right? If I want the 50th term, I have to compute 2 to the 50th, right? Let's see, let's do another one. Similar style, let's say b sub n is equal to 2 to the negative n. And let's do the same indexing. Let's start this one at 0 as well. Right, so we can use our previous work. That negative exponent just means everything gets put into the denominator of a fraction. So we have 1 over 1, or just 1, but then we get 1/2, and 1/4, and 1/8, and 1/16, and so on. Right, so there's another series. Let's do a couple more examples. Just get used to this idea. Let's look at c sub n is equal to 1 minus 10 to the negative n, where n is going to be equal to 1. I'm going to start this one at 1. All right, so let's write this one out. Maybe we can even make ourselves a little table here. We'll take it, we'll have a column for n. and then for C sub n, right? So when n equals 1, we're going to have 1 minus 10 to the negative 1, or 1 minus 1/10, or 1 minus 0.1 gives me 0.9. Right? When n equals 2, we get 1 minus 10 to the negative 2, or 1 minus 1 over 100, or 1 minus 0.01, which gives me 0.99. Right, now we might see the pattern. Let's do one more. 1 minus 1 over 1,000, or 0.999. All right, so I think now we see where this sequence is going. We would have 0.9, 0.99, 0.999, and on and on and on. Okay. Now, one thing we might notice about this sequence that we could have noticed earlier as well, I haven't said it, but this thing that we're setting up is satisfying everything that a function needs, right? That n is our input and the sequence itself is our output. So another way to think about a sequence is it's a function where the domain is simply the positive integers, or maybe 0 in the positive integers, right? And we're not going to get too deep in this. You could certainly index by other things as well. You could index by negative integers. You could start your indexing at 10 and go on from there. But in any event, generally speaking, it's going to be the positive integers, right? So it's a specific function that we could even graph. Right, so if I wanted to graph this function, we're at n is along our horizontal axis. This is not going to be the most exciting graph, right? At 1, so let's just put 1 up here. When we input n equals 1, we're getting something very close to 1. When we put in n equals 2, we're getting something even closer. When we get n equals 3, we're getting even closer, right? And at this point, I really can't draw it any closer. These are all dots just below 1, getting closer and closer, right? 0.99 is closer than 0.9, and 0.999 is closer than 0.99, and so on, right? So we don't create like a nice curve. The graph is just going to be some set of dots, right? But each one is still an input output pair. So this would be 0.99999, right? That last dot that I drew. Right, and so it still is the same thing a graph of any function is, the collection of input and output pairs. We don't typically graph our sequences, though there are times that graphing them is going to be nice. And while it is important to remember that they are functions, we use this alternate notation because we use them in different contexts. But it's perfectly reasonable. I mean, it's not just perfectly reasonable; it is correct to know that they are functions whose domains are at least some set of the integers, some subset of the integers. All right, a couple more examples. So let's do this one. D sub n is -1 to the n times 3 to the n. Okay, so this one's getting a little more complicated. Let's work out for various values of n. When n is equal to 1, we get -1 to the 1 times 3, or -3. When n equals 2, we get -1 squared times 3 squared. Well, -1 squared is just +1 times 3 squared is 9. When n equals 3, we get -1 cubed times 3 cubed. -1 cubed is -1, and then we're times 27, so we've got -27. We'll do one more. N equals 4, -1 to the 4th times 3 to the 4th. That -1 to the 4th becomes a 1, and 3 to the 4th is 81. So this sequence is giving us powers of 3, and the sign is switching back and forth. All right. So we call this kind of series where the sign goes from positive to negative and back and forth over and over again an alternating series. Okay, and these can be pretty important series down the line. So this is how that happens when we see this -1 to the n. Okay. In a similar way, let's just write I'm just going to go back to A. A sub n, let's do a very similar series, and let's just make it n plus 1 times 3 to the n. Well, what's going to happen is, when n equals 1, I'm going to use the work we just did. When n equals 1, this exponent right there, I think this lets me, yeah, that exponent right there, that was n, is now n plus 1. So it's, instead of to the first power, it's squared. So instead of being negative, it's going to be positive. When we get to n equals 2, instead of being squared, it's going to be cubed. And so it's going to be negative. And so we'll get the same thing, except that plus 1 up there changes when it's negative and when it's positive. So this new series, or sequence, will be positive 3, negative 9, positive 27, negative 81, and so on. So it's also alternating, but just starting with a different where the negative is. Okay. All right, one more example of this kind. Let's look at a, we can have sequences where they're defined differently depending on how what number we get. So for example, I'm just making something up, 1 divided by n if, let's say if n is a multiple of 3 and n squared otherwise, right? So when n equals 1, this is not a multiple of 3, we output 1. When n equals 2, this is not a multiple of 3, so we square it, we get 4. When n equals 3, this is a multiple of 3, we take 1 over that. When n equals 4, it's not a multiple of 3, so we get the square of that. When n equals 5, we square it. And when n equals 6, this is a multiple of 3, so we take 1 over it, right? So this is a strange looking sequence, 1, 4, 1/3, 16, 25, 1, 6. So it's like it's a list of all the perfect squares, except every third one suddenly becomes a fraction, right? Right. This one probably, can't imagine a use for this one, but there are certainly other kinds of things where you might have some use. We'll look at some of those and some activities further down the road. Okay, let's do a couple of other things. Actually, let's save that for another video. So let's end that one here. We've just introduced the idea of sequences. We've got some notation and a little bit of work seeing how we can write them out and given these explicit formulas. So we'll do a few other things in another video, but that is it for this one. Thanks, everybody.